We're going to take a look at gases. We're going to review some of the things that we should know. As you take a look at the diagram here, we have particles with arrows. Those arrows are just showing the straight line motion. These particles are in random motion, they're in continuous motion, and they are in straight line motion. We say that gases do not have a definite shape, they do not have a definite volume, meaning if I put it in one container to another, the shape of the gas would change because the gas always fills up its container. That's why it doesn't have a definite volume. So it takes the volume of the closed container. So if I take something, a gas that's in a 5 milliliter container, I put it into a container that's 500 milliliters. That gas went from a volume of 5 milliliters to 500. So it does not have a definite shape or definite volume. Terms that we need to know. We're going to start out with the kinetic molecular theory. All gases, all of them, whether they are ideal or real, and that's coming up in a moment, no matter what, they're all in this random motion. If you're talking about kinetic energy in terms of how they collide, when they collide, energy is going to be transferred from one to another. And that always happens, no matter what kind of gas it would be. Avogadro's hypothesis, if you remember, we talked a little bit about that. If you have the same temperature, the same pressure, and the same volume, be very careful because usually they talk about STP values, you're going to have the same number of molecules. Not necessarily the same number of atoms, but you will have the same number of molecules. So if I have hydrogen gas versus carbon dioxide gas, and I have 2 liters of each at STP, means I will have the same number of H2 particles as I do CO2 particles in terms of molecules. When we're talking about ideal gases, a few things that you need to know. One, that they really don't have forces of attraction, and their volume is negligible, really hardly any volume in comparison to its container. The particles are going to be far apart. That's usually what is asked of you. The ideal particles are going to be far apart. So you want to have particles that have the highest temperature with the lowest pressure, because that will make the particles far apart. Secondly, you want the particles that are the smallest. So elements such as helium and as hydrogen, those are your small particles. They have very little force of attraction. So those are the gases, helium and hydrogen, that are most ideal. If you want to talk about real gases, well, they do have forces of attraction. Their volume is significant in comparison to its container. The particles are going to end up being closer together. Again, you're going to have greater forces there. In order to get those particles close, the closer they are, the more real they are. You want to have the temperature low. That brings the particles closer. And you want to have the pressure high. Again, brings the particles closer. Secondly, you want the particles that are larger. So you would look on the periodic table and see which ones are the bigger gases. The bigger gases will have a greater force of attraction. Then we have the combined gas law, which is found on your reference table T. There is another video for you to watch that goes through combined gas law, so please watch that video to make sure you know how to solve those problems. Now, again, talking about gases in terms of our heating curve, here's really where you find your gas between E and F. You have, yes, you do have an equilibrium between D and E of liquid and gas, but if you're just looking for a gas, you would look between E and F. That's your only part that's your vapor.